In the previous video, we converted our image to grayscale, the foundation of computer vision. If you missed part 1, make sure to watch it first. Now, we're implementing the Sobel operator to detect real edges from brightness changes. This method implements the Sobel edge detection algorithm. It takes an input image and a threshold value, then analyzes brightness changes across neighboring pixels. The result is a new image highlighting only the strongest edges. First, we get the width and height of the input image. We cast them to integers because pixel dimensions must be whole numbers. These values let us loop through every pixel during edge detection. Next, we convert the image to grayscale. Sobel works on brightness values, not color, so we store the luminance data in a two-dimensional array. This is the Sobel kernel for detecting horizontal intensity changes. It's a 3x3 matrix designed to measure how brightness shifts from left to right. Negative values are on the left, positive values are on the right, and the center column is 0. When applied to an image, this kernel highlights vertical edges. This is the Sobel kernel for detecting vertical intensity changes. It measures how brightness shifts from top to bottom. The top row contains negative values, the bottom row contains positive values, and the middle row is 0. When applied to the image, this kernel highlights horizontal edges. Now we create a new writable image with the same width and height as the original image. This will store our edge detection result. Then we get a PixelWriter, which allows us to manually set the color of each pixel as we compute the edges. Now we begin looping through the image. Notice that we start at 1 and stop at height -1. That's because the Sobel operator needs a 3x3 neighborhood around each pixel. By skipping the outer border, we avoid accessing pixels outside the image boundaries. This keeps our convolution safe and prevents index errors. Here we initialize Gx and G to store the horizontal and vertical gradient values. These nested loops scan the 3x3 neighborhood around the current pixel. The variables kx and ky move from -1 to +1, covering all surrounding pixels. This allows us to apply the Sobel kernel weights to each neighboring brightness value. In other words, this is the convolution step where edge detection actually happens. Here we retrieve the grayscale value of the neighboring pixel inside the 3x3 window. Then we multiply that brightness value by the corresponding weight from the Sobel kernel. We do this separately for the horizontal kernel, Gxk, and the vertical kernel, Gyk. Each multiplication contributes to the total gradient in that direction. By accumulating these values, we measure how strongly brightness changes around the current pixel. Now we combine the horizontal and vertical gradients. Math Hypot calculates the overall gradient magnitude using the Pythagorean formula. The stronger the brightness change in any direction, the larger this value becomes. Then we apply a threshold. If the magnitude is high enough, we classify it as an edge and set the pixel to white. Otherwise, it becomes black. Finally, we write the result to the output image. Finally, we return the completed edge image. This method is called clamp, and it's a safety utility function. Its job is to keep a value within a specific range. We pass in a value along with a minimum and maximum limit. First, math minute ensures the value doesn't go above the maximum. Then, math max ensures it doesn't go below the minimum. This is especially important when accessing image pixels, so we never go outside the image boundaries. This method is a specialized version of clamp. but specifically for values between 0 and 1. Many visual calculations, especially animations and color values, must stay within this normalized range. First, math, min ensures the value doesn't exceed 1. Then, math, max ensures it doesn't drop below 0. This guarantees our calculations remain stable and predictable during rendering. This method is a specialized version of clamp, but specifically for values between 0 and 1. Many visual calculations, especially animations and color values, must stay within this normalized range. First, math.min ensures the value doesn't exceed 1. Then, math.max ensures it doesn't drop below 0. This guarantees our calculations remain stable and predictable during rendering. Here we create a new two-dimensional array to store the blurred result. It has the same width and height as the original grayscale image. Then we calculate the size of the blur window. Since the radius extends in all directions, the window becomes 2 times the radius plus 1 squared. This represents how many pixels will be averaged together. Now we loop through every pixel in the image again. The outer loop moves vertically through each row, and the inner loop moves horizontally across each column. For every pixel position, we'll calculate a new blurred value by averaging the surrounding pixels inside the blur radius. Here we start calculating the blur. First, we initialize a variable called sum to accumulate brightness values. Then we loop over the blur window using die and dx, which move within the radius in both vertical and horizontal directions. This allows us to visit every neighboring pixel inside the square blur region. We'll add each pixel's value to sum, and later compute the average. Here we calculate the coordinates of each neighboring pixel inside the blur window. We use the clamp function to make sure the new x and y values stay within the image boundaries. This prevents index errors when we're near the edges. Once we have safe coordinates, we access the pixel's brightness value from the source array and add it to our running sum. This continues until every pixel in the blur region has been accumulated. Finally, we divide the total sum by the window size to compute the average, creating the blurred pixel value. Finally, we return the blurred image data. This method checks whether a pixel has a strong edge neighbor. It takes the edge matrix along with the current x and y position. In edge detection, especially in Canny-style algorithms, weak edges are kept only if they are connected to strong edges. So this function helps determine whether a pixel should remain part of the final edge map. These nested loops examine the 8 neighboring pixels around the current position. The variables dx and die move from -1 to +1, covering all adjacent cells in a 3x3 grid. This allows us to check whether any surrounding pixel is classified as a strong edge. Here we skip the center pixel. When both dx and die are 0, we're pointing to the current pixel itself. Since we only want neighbors, we continue to the next iteration. Here we check whether any neighboring pixel is classified as a strong edge. In our implementation, strong edges are marked with the value 255. If we find even one strong neighbor, we immediately return true, meaning this pixel should remain connected in the final edge map. If no strong neighbor is found, we return false.